In the previous video, we have solved simple problems in protections of SCR. And that was the last topic in SCR, and now we are going to look into a next device called as Power Mosfet. Let us go and understand what Power Mosfet is. Let us go into the lecture. In this video, we will see how a Power Mosfet operates based on its construction, and also we will see some of the parameters used in Power Mosfet for characteristics are concerned. For further reading, you can follow the textbook on PS Pimbra between page numbers 20 to 24. These are all the contents of presentation. Initially, we will discuss the basics and features of Power Mosfet, and then we will go into the construction and principle of operation of Power Mosfet. Finally, we will look into the transfer and output characteristics of Power Mosfet. Now let us go into the basics of Power Mosfet. MOSFET is generally abbreviated as metal oxide semiconductor field effect transistor. The biggest advantage of MOSFET is it can switch at very high frequency, that is up to 100 kHz. Means that the fastness of this MOSFET is very high. Generally, we will compare Power Mosfet with Power BJT. The detailed comparison, we can see it in the next video. For understanding purpose, Power BJT is a current controlled device, whereas Power Mosfet is an voltage controlled device. In case of BJT, if I want to increase the collector current, the base current has to be increased. But because of this increase in base current, at the junction, the temperature increases. So, there exists a secondary breakdown problem in Power BJT, which is not associated with Power Mosfet. The features of Power Mosfet are the input current is very low and it is a voltage controlled device, whereas Power BJT is a current controlled device. The switching speed is very high in the case of Power Mosfet. And as I told that the secondary breakdown problem does not exist in Power Mosfet. The input impedance is very high, because of which the input current is very low. So these are all the features of Power Mosfet which attracts this device in certain applications. Let us go into the understanding of symbol and its construction. Power Mosfet are generally classified into two types. One is N channel and P channel. And it has three terminals, namely gate, drain and source. N channel symbol will have an arrow mark inside, whereas P channel symbol will have an arrow mark outside, which is very similar to NPN transistor and PNP transistor. So this is the symbol of BJT, N channel and P channel, of MOSFET N channel and P channel. If I look at the construction, it is also having an NPN type or PNP type. Now I am talking about N channel Power Mosfet, so it is an NPN type, which is very similar to that of the BJT. It has three terminals, gate, source and drain. The detailed structure is given here. This N layer is heavily doped, which is very similar to this N plus. N plus and this N are similar. This N plus means that it is heavily doped. We know that doping is directly proportional to conductivity and inversely proportional to depletion width. Whereas the case of the immediate next layer to N plus is P layer, which is a body also. So next to P layer we have N layer, and this N layer is divided into two. We call it as N minus and N plus. N minus in the sense it is lightly doped, and whereas N plus in the sense it is heavily doped. We know that lightly doped will have less conductivity and higher depletion width. So this layer is responsible for handling more amount of voltage, which is very similar to power diode. And this layer is also called as drift region, and the width of this region is based on the operating voltage of the device. And the source and drain are connected to the outer N plus layers, whereas gate is connected to the P layer or the body via a layer called SiO2 layer. SiO2 is silicon dioxide. So because of this silicon dioxide layer which present between the gate and P layer or body, we call this particular device as metal oxide semiconductor. Silicon dioxide is what we call it as metal oxide semiconductor. And the silicon dioxide layer is responsible for forming a capacitance between the gate and the body. So this capacitance plays a very important role in turning on of this MOSFET. Now let us go into the understanding of principle of operation of MOSFET. The same NPN structure is reproduced here. The N plus layers are connected to source and drain, whereas the middle layer is connected to, that is P layer, is connected to gate and body. Here you can see that there are two circuits. One is the blue circuit, other one is the red circuit. Blue circuit is what we call it as the gate circuit or control circuit, which is responsible for establishing the connection between drain and source. This red circuit is the power circuit through which we connect our loads. Say, as I told you already, that the silicon dioxide layer is responsible for forming the capacitance between the gate and the body. So this is very important for applications, or for you very important for operating principle. So there exists a capacitance between this gate and the body. Since this VGS positive is connected to gate and VGS negative is connected to body, this end of the capacitance will be positive and this end of the capacitance will be negative, which may be something like this. So more positive ions on the top and more negative ions on the bottom. Increasing this voltage VGS will increase the negative ions on this P layer. Further increase in VGS will increase the negative ions on the D layer. So there exists a channel between these two N plus layers via this new layer, and this new layer is what we call it as induced layer. So now this is also majority carriers of electrons, this is also majority carriers of electrons, and there exist more electrons at this side because of increase in this VGS. So this VGS is increased, this induced layer of more electrons are increased or placed at the P layer, which makes a connection established between drain and source, and current flows from drain to source through this channel or through this induced layer. So now the device has turned on. So this is how we turn on the power MOSFET, by increasing the VGS. So once I remove this VGS, this negative electrons will slowly vanish or slowly reduce, and again a depletion width will be formed in this P layer. It will restrict the flow of electrons from drain to source. So this is what all about the operating principle of the power MOSFET. Now let us go for the transfer characteristics. The transfer characteristics are plot between VGS and ID. VGS is gate to source voltage and ID is the drain current. Now if you look at, the drain is connected to the load via a VDD and the source. Once the device is turned on, there exists a current flow through this circuit, and this is what we call it as power circuit. But in order to turn on this, I have to supply my VG, gate voltage, as we discussed in the previous operating principle. So I'm going to plot VGS with respect to ID. VGS is the gate to source voltage with respect to ID. So this characteristics is what we call it as transfer characteristics. When we slowly increase this VGS and observe VD and ID, then we observe ID, increasing this VGS, observe ID by keeping this VDD as constant, or keeping this VDS or VDD as constant, vary this VGS, observe ID. So I will get a characteristics which is very similar to like this. So in this characteristics, again I repeat, in this characteristics we have VDD fixed, vary the VGS, observe ID and plot it, and we can see that at particular value of VGS, the current starts increasing very steeply, which means the device has turned on, and this voltage at which the current has risen very steeply is what we call it as threshold voltage of the device, and it is generally varied between 2 volts to 15 or 20 volt based on the operating voltage of the device. So this is what all about the transfer characteristics. Now let us move on into the output characteristics. In the case of output characteristics, we are going to fix the VGS. We are going to have VGS constant, and we are going to vary the VDS or VDD and observe the ID. So when I try to do that, when I assume that VGS is fixed to 1 volt and vary the VDD and observe the ID, I will get a characteristics which is something like this. Fix VGS to 1 volt, vary the VDD, find out what is the voltage across drain and source and observe the current. Till some point the current is very less and then it becomes constant. It increases and then it becomes constant. Now if I increase the VGS to 1 more volt, that means the VGS now I keep it as 2 volts and then again vary the VDD, observe VDS and ID plotted. Again at VGS is equals to 2 volt, the current is little bit more, the drain current is little bit more than the previous case and then it becomes constant. Similarly, when VGS is still increased, I can have a characteristics which is very similar to that. Similarly, for increasing the value of VGS, the drain current increases to a maximum value and then it remains constant. So if I put a load line here between the VGS characteristics, VDS and ID characteristics, and this is the point where the device is completely turned off. So this region is what we call it as cutoff region. This region is what we call it as cutoff region. If I look at this region alone, if I look at this region alone, the voltage and current both are increasing in a linear way. So this region is called as ohmic region. This region is called as cutoff region and this region is called as ohmic region. And if you look at this region where the drain current has saturated or has become constant, and this region is called as saturation region. So these three regions, cutoff region where the device is off, ohmic region where the voltage and current are varying linearly, and the saturation region where the device has completely turned on, or we call it as an active region. So these three regions are very, very important in the output characteristics of our MOSFET. In this video, we have discussed the construction, principle of operation, symbol of Power Mosfet and its transfer and output characteristics. And we have seen three regions: cutoff region, ohmic region and saturation region in the case of output characteristics. And in the next video, we will look into the switching characteristics and comparison of BJT with MOSFET in the next video. Thank you for your patient listening. Thank you.